All right, so today we're going to take a deep dive into machine learning.
Okay.
Specifically, I think model accuracy, getting those algorithms to actually learn and make good predictions. It's something that I'm really interested in.
Yeah.
I'm excited to kind of hear how all this works.
Well, it's a bit like teaching someone to ride a bike.
Okay.
You can explain the concept, show them how it's done,
Yeah.
but ultimately they need to kind of find their balance through practice and adjustments.
I like that. Yeah. So where do we even begin with this whole model accuracy thing?
Yeah.
What are some of the fundamental concepts that we need to grasp?
Well, one of the most important, I think, is the balance between bias and variance.
Okay.
It's like a classic trade-off in machine learning.
Yeah.
Too much bias, and your model oversimplifies things, kind of misses those crucial patterns in the data. Too much variance, and it becomes overly sensitive.
Okay.
Like, it's memorized the training data, but can't handle anything new.
So it sounds like we need to find that Goldilocks zone, not too biased, not too much variance, but how do we actually measure that?
Right.
How do we know if our model is hitting that sweet spot?
That's where the evaluation metrics come in.
Okay.
One of the most common ways to assess the accuracy of a classification model is using a confusion matrix.
Okay.
It's basically a table that shows you where your model's predictions went right and where they went wrong.
So it's like a scorecard.
Exactly.
From the model showing us how well it's doing.
Exactly. And from that confusion matrix, you can calculate all sorts of helpful metrics like accuracy, which tells you the overall percentage of correct predictions, and precision, which focuses on how many of the positive predictions were actually correct.
That makes sense. I imagine there are times when a model is just way off, right? Like it's either not learning enough or it's learning too much. What are those situations called?
Yeah, we call those underfitting and overfitting. Underfitting is when the model is too simple, like it hasn't studied enough and can't grasp the underlying patterns in the data.
Right.
Overfitting, on the other hand, is like the model has crammed for the test and memorized the training data, but can't apply that knowledge to new examples.
So if we imagine these scenarios visually, like what would those learning curves look like for a model that's underfitting, overfitting, or has that ideal fit?
That's a great way to think about it.
Yeah.
With learning curves, we're plotting the model's performance on both the training data and a separate set of validation data.
Right.
As it goes through the learning process, if you see that the model is performing well on the training data, but poorly on the validation data, that's a classic sign of overfitting.
So it's like it's getting a perfect score on the practice test, but failing the real exam.
Exactly.
Yeah. And what about underfitting? What would that look like?
In that case, you'd likely see poor performance on both the training and validation data.
Okay.
The model just isn't able to capture the complexity of the problem.
And that just right scenario, the one where it's like performing well on both sets of data, would be two lines that are converging nicely.
You got it. That's what we're aiming for, that sweet spot where the model is learning effectively and can generalize its knowledge to new situations.
We've talked about these kind of extreme cases, underfitting, overfitting. What are some of the things that can push a model towards those extremes?
Yeah.
Like what are the things that affect model accuracy?
Well, it all starts with the data itself.
Okay.
The quality, the quantity, and the representativeness of your data are absolutely crucial.
Okay.
If you're training a model on biased data, you're going to get biased results.
So it's like the old saying, garbage in, garbage out.
Exactly.
If we feed the model bad data, we can't expect it to learn anything useful.
Exactly. And then there are things like the choice of algorithm, like the complexity of the model.
Yeah.
Even the way you're tuning the model's parameters during the training process, all of these factors can play a role in how well your model performs.
It sounds like there's a lot to consider when you're trying to build an accurate machine learning model.
There is.
But before we get too overwhelmed, let's break down those problems of underfitting and overfitting a bit more.
Okay.
What are some practical remedies that we can use to address those issues?
Sure. When you have a model that's underfitting, one of the first things you might try is adding more features to your data.
Okay.
This gives the model more information to work with and can help it capture more complex patterns.
And so we're giving it a broader perspective, allowing it to see the bigger picture.
Exactly. Or you might try using a more sophisticated algorithm that's capable of learning more complex relationships.
Okay. And what about overfitting? How do you tame a model that's become too specialized to its training data?
One common technique is called regularization.
Okay.
It's like adding a penalty to the model's complexity,
Yeah.
discouraging it from memorizing the training data too closely, or you might try something called early stopping,
Okay.
where you halt the training process before the model has a chance to overfit.
That makes sense. So we're trying to prevent it from getting too bogged down in the details and instead encouraging it to focus on the bigger picture.
Exactly. And don't forget the power of data visualization.
Yeah.
Looking at your data visually through things like scatter plots, histograms, or even more complex visualizations can help you identify potential problems like outliers, missing values, or relationships between features that you might have missed otherwise.
So it's like giving ourselves a different perspective on the data that can reveal hidden patterns and insights that we might not have seen just by looking at numbers in a spreadsheet.
Absolutely. Data visualization is a powerful tool for understanding your data and for diagnosing problems with your model.
I'm really starting to appreciate how interconnected all of these concepts are.
Yeah.
From understanding bias and variance to using data visualization to diagnose problems and choosing the right techniques to address them.
It is.
It's like putting together a puzzle where each piece plays a crucial role in creating the complete picture.
And remember, building accurate machine learning models is an iterative process. It's about experimenting, learning from your mistakes, and continuously refining your approach until you achieve the desired results.
All right, we've covered a lot of ground here, and I'm feeling much more confident in my understanding of model accuracy. But I'm curious to hear more about how we can actually measure the performance of a model once it's built. What are some of those evaluation metrics you mentioned earlier, and how do they help us assess a model's strengths and weaknesses?
Let's delve into that in more detail.
Okay.
For classification problems, we have some very specific tools at our disposal, like the confusion matrix and metrics derived from it.
Great. Let's unpack those in the next part of our deep dive.
So picking up where we left off, let's break down those classification evaluation metrics.
Okay.
As we mentioned, the confusion matrix is a great starting point.
Okay. Remind me what that looks like again. It's a table, but what exactly does it show?
Yeah, it's a table that breaks down the results of your model's predictions into 4 categories.
Okay.
True positives, true negatives. Yeah.
False positives and false negatives.
So it's telling us not only if the model got it right or wrong, but also how it got it wrong.
Exactly.
Okay.
And that level of detail is incredibly valuable for understanding where the model's strengths and weaknesses lie.
Can you give me an example? How would this work in a real-world scenario?
Sure. Let's say we're building a model to predict whether an email is spam or not.
Okay.
A true positive would be correctly identifying a spam email.
Got it.
A true negative would be correctly identifying a legitimate email.
Okay, so those are the good outcomes. What about
Right.
the bad ones?
A false positive is when the model thinks an email is spam when it's actually not.
Okay.
And a false negative is when it misses a spam email and classifies it as legitimate.
And I'm guessing those different types of errors have different implications depending on the situation.
Absolutely. In our spam filter example, a false positive might be annoying,
Right.
but a false negative could be much more serious if it lets a dangerous phishing email through. That's a great point. So once we have this confusion matrix, what do we do with it? How do we actually use it to evaluate the model?
Well, from the confusion matrix, we can derive a bunch of other useful metrics.
Okay.
For example, accuracy, which we touched on earlier, is simply the overall percentage of correct predictions. It's a good starting point, but it can be misleading in situations where you have imbalanced classes.
What do you mean by imbalanced classes?
Imagine in our spam filter example, only 1% of the emails are actually spam.
Okay.
A model could get 99% accuracy by simply predicting that every email is not spam.
So accuracy alone doesn't give us the whole picture. What other metrics can we look at?
That's where precision and recall come in.
Okay.
Precision tells you of all the positive predictions the model made, how many were actually correct.
Yeah.
Recall, on the other hand, tells you of all the actual positive cases.
Right.
How many did the model correctly identify?
So precision is about being really sure of your positive predictions, and recall is about making sure you catch as many of the true positives as possible.
You got it, and depending on your application, you might prioritize one over the other.
That makes sense, but is there a way to get a single metric that combines both precision and recall?
Yes, we have something called the F1 score,
Okay.
which is the harmonic mean of precision and recall.
Yeah.
It gives you a single number that represents a balance between the two.
Okay, so we've got accuracy, precision, recall, and F1 score. Are there any other important metrics we should be aware of?
There's also something called the ROC curve,
Okay.
which stands for Receiver Operating Characteristic.
Okay.
It's a graph that shows you how the true positive rate and false positive rate change as you adjust the classification threshold of your model.
So it's like seeing how the model's performance shifts as we make it more or less strict in its decision-making.
Precisely.
Yeah.
And the area under that curve, the AUC, gives you a single number that summarizes the model's overall performance across all possible thresholds.
Wow, it seems like there's a whole world of metrics out there for evaluating classification models.
Yeah, there is, and choosing the right metric or combination of metrics really depends on the specific goals of your project and the costs associated with different types of errors.
Okay, so we've learned how to evaluate a model once it's built. But let's take a step back and think about how we can estimate a model's performance before we even deploy it. How can we get a sense of how well it will generalize to new unseen data?
That's a crucial question.
Yeah.
And there are a couple of powerful techniques we can use.
Okay.
Cross-validation and holdout sets.
Okay, tell me more about those.
With a holdout set, you essentially set aside a portion of your data that the model never sees during training.
Okay.
Then once the model is trained, you use that holdout set to evaluate its performance.
So it's like a final exam to see how well it handles brand new data.
Exactly. And what about cross-validation? How does that work?
Yeah. How does that one work?
Cross-validation is a more sophisticated technique where you divide your data into multiple folds.
Yeah.
You train the model on a subset of those folds and then evaluate it on the remaining fold. You repeat this process multiple times, using different folds for training and evaluation each time.
So it's like giving it multiple practice tests to get a more robust estimate of its performance.
Exactly. Cross-validation is particularly useful when you have limited data, as it allows you to make the most of the data you have for both training and evaluation.
This is all fascinating stuff, but I have to admit it can feel a bit overwhelming at times. Are there any simple rules of thumb or guiding principles we can keep in mind as we navigate this world of model accuracy?
One of the most important things to remember is that there's no magic bullet when it comes to machine learning. There's no single algorithm or technique that will guarantee success in every situation.
So it's more about understanding the tools at our disposal and choosing the ones that are most appropriate for the task at hand.
Absolutely. And it's also about being willing to experiment, to try different approaches and to learn from both your successes and your failures.
That's a great reminder. Machine learning is all about iteration and continuous improvement. And speaking of improvement, I'm curious to hear more about how we can actually make our models better. What are some strategies for boosting accuracy and addressing those pesky problems of underfitting and overfitting?
Let's delve into that in the final part of our deep dive.
So we've explored how to evaluate a model's performance, but what can we do when our model isn't quite hitting the mark? How do we actually go about improving its accuracy?
Well, as we've touched on before, underfitting and overfitting are two of the most common culprits when it comes to poor model performance, and thankfully there are quite a few strategies we can employ to combat these issues.
Okay, let's start with underfitting. What are some of the go-to techniques for dealing with a model that's just not learning enough from the data?
One of the simplest approaches is to add more features to your dataset. Think of it like giving the model more pieces of the puzzle to work with. This can help it capture more complex relationships and patterns within the data.
It's like we're giving the model a broader perspective, allowing it to see the bigger picture, right?
Exactly. And sometimes it might be necessary to switch to a more sophisticated algorithm. If you're using a linear model on data that has a lot of nonlinear relationships, you're likely going to run into underfitting issues.
So it's about matching the complexity of the model to the complexity of the data. Like you wouldn't use a hammer to screw in a light bulb. You need the right tool for the job.
Precisely. And sometimes the solution might be as simple as giving the model more time to learn. Increasing the number of training epochs can sometimes help the model converge to a better solution.
Okay, so we've added more features, potentially switched to a more complex algorithm, and given the model more time to train. What if it's still underfitting? Are there any other tricks up our sleeve?
It might be time to reevaluate the data itself. Perhaps there's some inherent noise or inconsistencies in the data that are preventing the model from learning effectively. Data cleaning and pre-processing can go a long way in improving model performance.
That's a great point. It's easy to get caught up in the model building process and forget that the foundation of it all, it's the quality of the data. So garbage in, garbage out, as they say.
Exactly. Now let's shift gears and talk about overfitting. This is where the model has essentially memorized the training data, but struggles to generalize to new unseen examples.
Yeah, we talked about how this shows up in the learning curves, with that gap between the training performance and the validation performance. What are some strategies for tackling this overfitting problem?
One of the most widely used techniques is called regularization. It's a way of adding a penalty to the model's complexity, essentially discouraging it from getting too attached to the specifics of the training data.
So it's like we're telling the model, don't get bogged down in the details, focus on the bigger picture.
You got it. And there are different types of regularization techniques, each with its own nuances and benefits.
Are there any other techniques for preventing a model from becoming too specialized?
Another approach is called early stopping. As the name suggests, it involves stopping the training process before the model has a chance to overfit. We monitor the model's performance on a validation set during training, and when we see that the performance starts to decline, we halt the training.
It's like we're saying you've learned enough, stop cramming.
Exactly. And sometimes the solution to overfitting might be as simple as reducing the number of features in your dataset. If you have too many irrelevant or redundant features, it can actually hurt the model's ability to generalize.
So it's not always about more data. Sometimes it's about being more selective and choosing the features that are truly informative.
That's a crucial point. Again, data visualization can play a key role here in helping you identify which features are most relevant and which ones might be contributing to overfitting.
I'm really starting to see the value of data visualization throughout this entire process, from understanding the data to building the model to diagnosing problems and refining our approach.
It's an invaluable tool in the machine learning practitioner's toolkit. And remember, all of these techniques we've discussed are just a starting point. There's a whole universe of methods and strategies out there, and the best approach will always depend on the specific dataset and the goals of the project.
You know, this deep dive has been incredibly insightful. We've covered so much ground, from understanding the fundamentals of model accuracy to exploring the nuances of evaluation metrics and delving into techniques for addressing underfitting and overfitting.
And remember, the key takeaway is that building accurate and reliable machine learning models is an iterative process. It's about constantly experimenting, learning, and refining your approach.
That's a great point. There's no magic formula, no one-size-fits-all solution. It's all about understanding the tools at our disposal and being adaptable in our approach. Well, this has been a fantastic journey into the world of machine learning model accuracy. We hope you've enjoyed the ride and feel equipped to tackle your own machine learning challenges with a newfound confidence and understanding.